All right, just before we get started, quick reminder, I'll just write it down here. So your assignment number 1, it is due tonight, right? Today is Wednesday, right? So please make sure you submit your best attempt to claim the credits. Of course, the policy is you should really submit your best attempt, no matter how partially it might be. You have done the implementation or the proofs, right? Just do your best. And then after the submission deadline tomorrow, maybe in the afternoon or in the evening, the latest, I'm going to release the solution for both the programming and also the written part for the solution. For the depth first search and also the 2 proofs, I'll release them. Please go over them as much as you can. And on Friday, we can go over parts of the solution, especially the programming part. There's certain part I would like to highlight together with you on Friday, right? We'll meet in person on Friday here. And then for next Monday, right? I'm just doing some final detail just to make sure everything will actually just work. But for now, it's confirmed. It's going to be 50 minutes for your test on Monday. And then it's going to be from 4:30 p.m. to 5:20 p.m., right? As I said last time, 50 minutes. And it's going to be in Williams Moore Center. And it's going to be either 106 or 108. So please let me confirm a little bit later. But definitely Williams Moore Center, nowhere else, right? I already reserved the room. I just need to confirm some final detail and set a booking, right? Williams Moore Center. And once you arrive on Monday, Monday, I'll write Monday here. So it's going to be Monday, which will be October 27th. Okay, next Monday. And then once you arrive, so please just wait outside. Me and the TA will set up the room. We'll let you in as soon as we are ready. Good. All right, apart from that, I think that's it, right? So today is really completely led by your question. You can ask me anything. I haven't really finishing design the question just yet for the test, so I cannot really tell you exactly what's there. But I'm pretty sure I will put some question about the edge list graph for programming. All right, that one's for sure. So that one can make a note, and definitely what's the best preparation for you? Just do the assignments, right? Yeah, and then, just ask a question, please, and then I'll try my best to explain. If there's anything that I'm not exactly prepared for, I'll definitely follow up, by maybe some announcement to everybody. I'll make sure it's properly addressed before the test. All right? So guys, take your time. It's really your time. I don't mind going up to 18 minutes. If really no question, then we say goodbye earlier, right? Okay, take your time. Okay, I can wait. Yeah.
Is a breadth first search on the test?
Okay, it's a breadth first search on the test. Good question here. I think we covered just a little bit on Monday. Let me also confirm that, right? So let's just go there. I can also write it down in a moment. The short answer is yes, it will be there, but only the basic part. So what do I mean by basic? I'm also going to release the lecture recording very soon. I'm still just trying to do many other things, but I'll definitely make sure I prioritize that today. So let's go all the way to the breadth first search. Give me a moment. Okay, there we go. Okay, let's see. Okay, I think you have to study slide number 41 and 42. That'll be enough. And plus the little example we did, remember on Monday, on the iPad notes. Once you release it, you can just study for that one. Very basic stuff for breadth first search, right? Mm-hmm. And of course, for the slides, I can also mention that briefly. So for the slides, if you go to the lectures page, starting from lecture 1, right? DBC, modularity, ADTs, asymptotic analysis, self-balancing binary search tree, and also the graph, up to 42. Okay, I'll put it down. Actually, they should be on a different desktop. There we go. Okay, I'll put it here. So for your graph, the PDF lecture slides, up to and including slide 42. All right. But since you only got 15 minutes for the test, right, I'll make sure it's appropriate for the 15 minutes test. But you can definitely expect there will be parts that where you have to import the projects into the Eclipse and then complete certain part like an A1 and then export the project and for submission. And then you will also need to make sure you bring your mobile phone, right? You're gonna do some dual mobile verification as well because you also need to log into eClass to do some questions there too. Pretty much like what I said on Monday. Okay. Yeah, guys, take your time. No rush. So while you're thinking about your question here, so basically when we resume the lecture next Monday, sorry, not next Monday. Of course, we'll do the test next Monday. When we resume the normal class on Wednesday. So I think before the end of the semester, I want to do a few more things, definitely about the graph. So I want to finish off the two other implementation strategies for graph. One of them will be adjacency list. The other one will be adjacency matrix. So these are the more commonly used ones, but they're kind of built on top of the edge list concept. So what you did in assignment number 1 is going to pay off as well. So two more strategies, and then I want to finish off breadth search, and then I want to talk about topological sort, which is a very practical algorithm to study. And then I want to talk about the Dijkstra's shortest path algorithm. That's going to be a very interesting one to study. After this, I will try to do either 1 or 2 minimum spanning tree algorithm. I will see how the time will permit. After that, I want to do at least 1 dynamic programming algorithm to also introduce the programming paradigm. Okay, that's pretty much it, right? We just want to make sure anything we cover, we want to go as in-depth as possible. Also, you have the ability to really implement something similar on your own beyond this course. I think that will be a very good takeaway for you. Okay. Please.
Is it possible for us to run through an example of doing an inductive proof today?
Sure. You mean the one? Do you want to do the ones we did earlier, or you want to do something new?
Something new would be preferred. Yeah.
Okay. Inductive proof. Why don't we try? Okay, I think what we can do is this. Okay, give me one moment. Okay, guys, bear with me 1 minute. I'll set it up. And then I'll see which one I can choose. Just give me one moment. Let me just first of all find the starter page. Okay, just give me 1 more minute. I should be able to finish setting up. So I think what I can do is I can definitely go over the base cases, and then I can go over some strategy, and then there will be some critical part. Maybe I can leave like an exercise you can also try, and then I'll release a solution as well after today, right? So you also get a chance to practice. Okay, let's do this one here. Oh, sorry, forgot to switch. So my bad. All right. Okay, that's one of the example we did in the class. What about we talk about the connected part? Okay, let's say we talk about this. So the question reads like this. Okay, so given some graph, undirected, and then we got a number of vertices being n and number of edges being n. And then we say that given that G is connected, so first of all, just about a language issue, right? So you can think about the way to read this is, oh, sorry. The way to read this is like this. We are saying that if G is connected, we can revisit about what being connected really means. That implies, given that this is true, then we know that the right-hand side, the consequence is true. Larger than or equal to n minus 1. Of course, you can remind yourself, m here is the number of edges. It should be at least the number of, at least as many, n minus 1. All right? And then, so what we want to do is prove this, right? So this one here, usually if you want to prove a property about graph, you believe that's a theorem, it's something that's provable, you will use mathematical induction, almost all the cases. If you want to somehow show the property is not really true, all you got to do is, okay, let me just say in general. Okay, so it's good to review the strategy here. In general, given a graph property, okay, if, or to prove it true, to prove it, you can use mathematical induction, which we're going to do in this case. Mathematical induction. To disprove it, you have to give the so-called witness, give a witness, like a graph, that's going to violate the property. So you can show that the property doesn't really hold as a theorem always. To give a witness graph G prime, just a different graph that violates the property. Okay, so that's the principle you want to keep in mind. Okay, so in the question, I'm not saying just for the test, maybe in the exam, if I give you a property, I may not tell you to prove it, I just say now prove or disprove. In which case, you may want to think about, I would say typically you may want to try to disprove it to see if you can find any example that's gonna violate the property. If you don't seem to be able to find it, maybe you will try to prove it. Okay, depends on which way you want to go. Okay, let me make this one a little bit smaller, and then let's now sketch. I think for induction proof, really the most creative part will be really the very last step, right? Other than that, everything else will be very kind of a routine. But let's now see how we can do it. Okay, let me just make this part smaller so we get enough space. Okay, I'll make it a little bit smaller. Okay, so there will be several steps. And also I'll structure similar step also in the assignment 1 solution. So when you look at the solution, take a look, and then you can also try to redo it as well. Okay, so there will be several parts. Part number 1, base cases. Okay, and of course number 2 will be, you want to state the inductive hypothesis. Inductive hypothesis. And number 3 is where you want to prove the inductive case. It's a little bit like in Java, if you want to program a method recursively. First of all, you put an if then else for base cases. And then you somehow have certain recursive call on some strictly smaller input. Let's say you want to run a recursion on a tree. You may have 2 different recursive calls, one on the left subtree, the other one on the right subtree. And then that's more like inductive hypothesis. You assume the recursive call is going to work. The step number 3 is about how do you combine the result from the various recursive call and make them work together, right? So that's number 3 is going to be usually the most complicated one. Okay, let's now do 1, 2, and 3. For number 3, I'll try to do a little bit of hand waving and sketch a little bit, and I'll give you definitely the solution, write it out properly when we after the class today. Okay, but let's try. So base cases. So before that, I can also say something here. We're basically doing inductive mathematical induction, and usually you will have to say what is the targets for you to do that mathematical induction on. You might do the mathematical induction on the number of vertices, in which case you got to consider 1, 2, 3, 4, 5, etc. You might do the induction on the number of edges, right? Depending on which one you're doing. Okay. So let's say in this case, we want to say that. So proof by induction on the value of the number of vertices, which we know in this case it is simply equal to n, and it will be larger than or equal to 0. When it is equal to 0, we got an empty graph, right? We start with the base cases. And for base cases, you can try maybe just show about 2 or 3, right? So maybe in the test or exam, if I really want you to just do base cases, I'll specify exactly how many base cases you have to do, right? But typically we can try 3, okay? That's what I did for the assignment 1 solution as well. All right, for base cases. So here, when the number of vertices is simply equal to 0, that means we have an empty graph. And let's revisit what does it really mean for the graph to be connected. A graph is connected if every pair of vertices has some edge connecting between them. Some path. Not necessarily directly connected, but some path, which will be a sequence of edges, right? Some path connecting between them. Another way to see this is like this, okay? So if I got some non-empty graph, let's say if I am able to find between any pair of vertices, I'm able to have a path connecting between them, it's connected. If you are not able to find any 2 vertices, they are not connected. That's another way to show that the graph is connected. I'll write it down. Alternatively, if there is no pair of vertices with no path between, then the graph is connected. All right, so this will be very useful as a base case, right? So now if you look at that, the empty graph where we got V here and also we got edges is also equal to 0, okay? Empty graph, it is connected trivially because you cannot find any violation. You cannot find any 2 vertices that's not connected. There's simply no violation case, okay? No violation pair of vertices can be found. All right. So in this case, we can do some quick math. So V here is V here is n, E here is m. So 0, so what we want to show is the m larger than or equal to n minus 1. M here is 0. N here is also 0. 0 larger than or equal to minus 1? True, trivially, right? So that's easy to judge. But I think that this base case is also valuable to mention because empty graph is a very special case for where many property, all property will just satisfy trivially. Okay? So in some cases, maybe I'll simply disregard the empty graph to consider in the property, in which case your base case should really start from maybe vertex being 1. Okay? Let's now move on with one more. Okay, so you put it here. Okay, let's now talk about when v is equal to 1. Let's say when v is equal to 1. That means you have basically a single vertex, right? All right, so here, so that's what you have. Is this graph connected though? You're basically asking, well, in some ways it's like a special case. You only got one vertex over here. So a vertex over here, so to really connect, since we're only talking about connection, there's nothing about cycle, right? You don't have to worry about it. So in this case, for that to be connected, you may just have a self edge, like a self loop right here. So this one here is going to be v and v, that's going to connect it, all right? So now in this case, the number of edges is simply equal to just 1, all right? So that one there is also going to satisfy the property, right? You can see this is, again, number of edges is m, and the number of vertices is actually n. So you can see 1 larger than or equal to 1 minus 1. That's also true, right? Yeah, base cases are usually very easy to plug in and actually show. There shouldn't be any trouble for you as long as you plug in the right number, okay? And base cases are usually just some very simple graph, like with 1, 2, or 3 vertices. For you to draw, to really draw something that's going to satisfy the property, it's not difficult, okay? So, all right, let's now talk about inductive hypothesis. Okay, so this one here, we're basically just going to go back to this particular question here, just state it again. But we want to be more careful about the size. Usually we use the value k, right? K is just some variable. You can use other variable if you wish, okay? So here we're just saying that for a graph, undirected graph, let's be careful, because we talk about undirected. For a undirected graph with k vertices. Okay, so we are really saying the number of vertices is simply equal to k. And also k here should not be the base case anymore. So it should be at least larger than 1. Because in the base cases, we talk about 0 and 1. So here, assuming that k is larger than 1. All right? And given such graph, we know that if, you can either say if the graph is connected, then the number of edges is larger than or equal to k minus 1. Right? That's a property. So here we're just substituting. So here, rather than having just n here, we just say k specifically, right? K minus 1. And also m here, I just say the number of edges. They're really the same. Okay, so that's the inductive hypothesis, which we should use at some point. All right, so that's inductive hypothesis. Like that. All right. So now for the final bit, I would say usually be very useful to somehow visualize that a little bit. That's something I'll also show to you, also for your assignment number 1 solution. And we also did some example earlier in the class. So think about the inductive hypothesis can give you a certain graph without the exact shape, but it gives you some property about that particular graph. So what this inductive hypothesis gives to us is this. So think about, we have, okay, like here. Think about we have some graph over here, and it's based on the inductive hypothesis. And this particular graph has k vertices. And then we say that the number of edges should be larger than or equal to k minus 1. And also, this graph over here is connected. And you can also say the k here is larger than 1. All right, so let me just say that again. It's very important for you to understand very well about what the inductive hypothesis really gives you. Usually it's very strong enough for you to just make some small extension. Okay, so the inductive hypothesis that we got from earlier tells us, number one, we got k vertices, and k is larger than 1. And then the property itself tells us this, given that it is connected. All right? That's what we know about this particular kind of abstract graph. We don't know the exact concrete shape of the graph, but we do know some property about the graph. That should be enough for us to argue the property for some strictly larger graph by just adding one vertex. Since we are doing mathematical induction on the number of vertices, so when we consider something bigger, just add in one more vertex. All right? If you try to do the mathematical induction on the edges, you got to add one more edge, right? It's different. All right, so here is a question for you, okay? Let's say we are trying to add in a new vertex. Let's call x. All right? So we are basically trying to create a larger graph with k plus 1 vertices. And the plus 1 over here really is about the x that we are trying to add to the existing graph, right? But it's very important to make sure such that, okay, such that, I'll put a star here, I'll put it here, I'm just running out of space, okay, I'll put a star here, such that the new graph is connected and the number of edges, I'll put E prime here. So you can think about the E prime here is the edges after the extension, right? So the E here is the number of edges before the extension and after the extension, right? So this one here should be larger than or equal to the number of vertices after the extension minus 1. All right? And let me say one more thing. A hint for you. For this part over here, about the number of vertices, right? That one there, you know that is going to be k plus 1. All right? So what remains to be done, that's something I'll leave to you. You want to think about how can you use this visualization here, maybe by making some connection, maybe by adding some like a new edge. After doing that, how can you show that this equation here is inequality here is also true? That's what's outstanding. Okay? So this is the part I'll leave that to you. And I'll definitely give you a solution. Okay? So think about for this part here. Show that this is true. And somehow you have to use the inductive hypothesis to show that it is true. Okay? So what remains to be done in this proof here, we have done basically about 80% or almost 90%. What remains to be done is you somehow want to think about how you can connect the existing graph guaranteed by the inductive hypothesis with the new extension. How are they supposed to be connected? And then using that connected strictly logic graph to show that this inequality is the case. That's what you're going to do, right? This is kind of the pattern you will see for almost every proof, all right? Hopefully that kind of helps. Okay, good. Yeah, so try this out and then I'll give you the remaining step, maybe later. Okay, exercise. All right, guys, next question. Yeah, follow up or?
Follow up. For the base case of the one vertex, if you didn't have any edges, would it still technically be considered connected?
Connected. It's a very good question. I think in this case, we are not really considering it because somehow you got vertex. Well, it's a very good question. Let's say this. I think this is the kind of thing I think to be very careful, maybe in an exam, I may have to clarify to say, okay, if you got one vertex graph, maybe that should be considered connected or not connected, right? Let's think about this, okay? It's a good question. When we have only a single vertex, one vertex graph, okay, we're asking whether or not it is connected. So we already talked about the case where it is not connected. That's why we want to add an edge, right? Let's say it is actually connected. And the consequence is, that means we got number of vertices will be 1, and the number of edges will just be 0. Okay? Now, would the property hold? Right? Let's see. The property say, given that it is connected, you should really have the number of edges larger than the number of vertices minus 1. The number of edges, 0, larger than or equal to the number of vertices minus 1. So this one seems to be still holding. So you can go either way. Yeah, I think whether or not like a single noded vertex graph is really connected, it could be a little bit up to our definition. So I would say, in this, as far as this property is concerned, it doesn't matter which way you go. Yeah, but I think in the exam, if this definition really matters, I will clarify that explicitly. Yeah. So guys, by the way, I'm just curious, while you're still coming up with your question, right? I want to say something very quickly for your assignment number 1, programming part. It's more about exception, right? Because exception was something you learned back in 2030, so not exactly 31.1, not even 21.1 stuff. I just want to see if you can understand that, right? So let's say this. It might be nice to mention this briefly as opposed to just Friday, okay? If I have a try and catch block, okay, and then over here I say some exception. And then maybe E, right? Like that, some exception. And of course, this is some class you will have to create by yourself. And you can easily do this. You can just move your mouse over the exception that's kind of red underline, and then one of the options is you can create that exception class. I can show you that briefly on Friday, but that's something I thought you would pick up from 2030. And now here's the question, okay? So I'll give you 2 alternatives. This is one. Oh, let me just make some box first. I think talking about one of them should be enough. Okay, just put it here. Okay. And then let's say I'm calling some method. Let's say if I have some graph objects, and then I'm calling some method with some arguments, right? Let's say that's the only line of code. And then after this, I can either put the fell assertion here, okay? Let me compare 2 of them in parallel. I think that'll be better. Okay, let me make it a little bit smaller. Okay, let me put another one here. Oh, let me make it smaller like that. There we go. Okay, and for this one here, for the second version on the right, I want to modify where we put the fell. Rather than here, okay, I'm going to move the method just a little bit up, right here. And I'm going to put the fell right here. You may have seen both patterns in the starter test in A1, all right? So why don't we try to clarify what's going on? Is it a question or you want to answer? Yeah, let me let your fellow student think about it. Yeah, no, I'm pretty sure you know the answer, right? So I think it's important for you to kind of see what the test case is really telling you in both cases, right? They're giving you different hints about the method itself, all right? Okay, maybe I can just give you one more. Let's say we are passing some arguments, let's say v1, some value 1, some value 2. Go ahead.
So the one on the left is telling you that it's not supposed to throw that exception. The one on the right is supposed to throw that exception. So if the one on the left, you run that piece of code and that exception is caught, it's gonna like trigger the catch block and you can see that
Yeah.
the test failed, right? Meaning that if you run that method and it's throwing that exception, it's not correct, right? Whereas the one on the right, you can see that there's two lines that are both inside the
Yep.
block. So if you run that code and it doesn't throw that exception, you've done something.
Yeah. Good. You want to say something? Yeah, before I just summarize. Yeah.
Isn't this so that this like both of these used for cases where edges where the first one is for the ones that is within the boundaries of the edge locations, and the other one is for outside?
You can think, in some way you're basically specifying, you're basically saying something about the same method M, right? But you're saying that for V1, it's going to behave differently from V2. You're basically, in some way you're setting some boundary for the method, yes, in some way, yeah. Let's be a little bit more precise. And I think your fellow student also said it pretty much spot on. I'm just gonna repeat and paraphrase what he said. So we're really calling the same method here, right? The same method, right? But with different value. Value 1 versus value 2, okay? So in this case over here, think about when the exception might occur. Exception will occur, think about execution flow. Exception will, if the exception occur, that means you're gonna fail the test. So this tells you, fail the test if the some exception occur. The only line that can actually trigger that exception is from here, right? So that means if this line here trigger that exception, and then if this one throws some exception, and then we're going to fail the test. That tells you that when you call the method on V1, you are not expecting to see that exception. And if the exception occur, you should fail the test, right? That's the logic, okay? So that means not expecting some exception when calling M on V1. And the right-hand side is kind of the flip side, right? It's saying something different, okay? So here, if you're able to go from this line to the next line, that means nothing wrong happened, no exception occur. Because whenever an exception occurs from the method call, it's going to disrupt the flow of the method, right, of the line. So now that means if you're able to go from here to here, so that means there's some exception not thrown. All right? So this fail over here tells you that fail the test if some exception did not occur. That means we're expecting the opposite to be expected, right? So that means we are expecting some exception when calling the method n on v2. All right? So you actually see both patterns in A1. So this will kind of give you some hints about how you're supposed to design the boundary or like a precondition for your method, right? For example, let's say if you're trying to, if you're trying to, let's say, add a new vertex, you got to make sure the vertex does not already exist, right? If you're trying to add some existing vertex, then you may expect some exception, right? Yeah, so this part here is not really 3101, but I think it might be nice to brush up, right? Something we are supposed to know from 2030. All right? Guys, okay, let's see. Why don't we take a short break, all right? About nearly halfway, more than halfway. Take a short break. We can all right. Guys, any more questions? Yes.
When you do the final destruction, you each have multiple rotations.
Uh-huh. Multiple rotation. You want to go over that?
Yeah.
Okay, we can do that. Give me one moment. I can set it up. So the question was about a self-balancing tree. Let me just get it. Give me one moment. Delete 80, right? Yeah, okay. One moment, I'll set it up. That's one, and then I'll just get the description as well so that can help us. I'll put it alongside. Okay, try node. Okay, maybe I'll bring out the slides. That might be easier. Okay, bear with me 1 more minute, and then we'll get started with this example. Okay, the one we should look at for the slides would be about after deletion. Okay, let me just copy this one here. Okay, hopefully that will work. Okay, let's see. Okay, actually that's not exactly working, but okay, we can switch back and forth, okay? So to do this example here, again, we can do just enough, so you can also try to complete it as well, okay? So for this one here, why don't we try to do it along the way? So why don't we try to insert all the nodes into the binary search tree, right? Let's do that first, and then determine if that's balanced. Okay, why don't we do that? So that one there, we start with 50, 25, 10, 30, 5, 15, 27, but feel free to just watch me doing it and let me know if I do anything wrong. 75, 60, 80, and also 55. External, 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 and external here, external, external, external. Right? Hopefully that's correct. And then we want to determine if this initial tree is balanced. 0, 0, 1, 0. The maximum is 1 plus 1, we get 2, right? 0, 0, 1, 2 and 1, maximum is 2 plus 1, 3. 0, 0, 1, and then we got 0 here. 1 and 0, the maximum is 1 plus 1, 2. Okay, 0, 0, 1, 0. Maximum 1 and 0 is 1. 1 plus 1, 2. Okay, 0, 0, 1. Maximum among 2 and 1, 2. Plus 1, 3. 3 and 2, maximum is 2. 3 and 2, maximum is 3. Plus 1, 4. 4 and 3, maximum 4. Plus 1, 5. All right, if you double check, you can see all the, for all the nodes, is left subtree and right subtree, the height is the difference no more than 1. Right, good. Right, just make sure you can do it. Okay, it's balanced. It is balanced. And then we're going to delete 80. All right. So delete 80, we're basically just going to get rid of 80 right here. Right? You can basically remember deletion, that's something you also need to review. Right? You're basically going to do a binary search, you will find that 80 is right here. But somehow we are lucky, the 80 here is really just the one has 2 external nodes as child. So we can just delete it. Okay. So after this, let me see if I can copy the tree without creating a mess. Okay, so let me do this one here. Okay, that's good. Copy here, undo. Okay, good. Right here. And I'm just going to delete 80. And after 80 is deleted, that part there is going to be converted into an external node. And of course, it's going to be 0. Right? And then let's now update the heights. So here, for the heights, 2 and 0, maximum is 2, plus 1, we still got 3. So we are fine. Okay? However, you can see this one here is already not balanced. Right? Not balanced. All right. So what we should do now is, now let's see, according to the algorithm, what we should do. Okay. You know what? I think it will be really just much better if I don't have to switch like that. I do want to annotate for you. Give me one moment. I think I have a copy of the slides somewhere on my iPad. I'll dig it out. If I cannot, we can still live with it. That's okay. Okay, this might be it. After insertion and then deletion. Okay, I find it. I think this will be much better. Okay, let me take a screenshot and then I'll put that in a new page and then we can go over that briefly just to see what are the steps. Okay, and then like that. Okay, good. Let me now go back there and then go back to here. All right, good. So let's now turn to a new page. There we go. All right, so that's also from your slides, right? Just the steps. Let's see exactly what we should do, okay? So what we should do is, so at least one node becomes unbalanced. Okay, we do see that node, that's unbalanced. All right, so, and then we're gonna identify that node, really. So the node that's unbalanced is going to be A. Okay, let's identify what's A. In this case, this is A. Agree? Because you can see the node A, the left child has the height 2. The right child has the height 0. So it's more than 1. So that's the lowest node that's unbalanced. Okay, that's A. And then how do we find B and C? So we can do a tri-node restructuring. So what about B? According to the definition, the B here will be the taller child. Okay, so here, if you look at A has 2 children, 1 and 1, and choose the taller one, 60, right? Taller one. So this one here would be B. Okay, and then what about C? The C here, it will be involve a little bit more decision making, but it's not too bad. Okay, so you basically have to see, okay, if they have different heights or they have the same heights. Okay, first of all, let's check to see which case it is. So for B here, we got actually 2 children. You can see we got basically underneath it, we got either 55, we got this one here. You can see they got 1 and 0. So they actually got different heights, right? Different heights. If there's different heights, we actually have to go for this one here. And then C should be the taller child. Okay, choose the taller one. All right. So what we should do is choose the taller one. But you're following through faithfully right here, right? If they got different heights, and then choose the taller one. If they have the same height, you will choose the one that's going to slant the same way, right? Are you following so far? All right, good. So once we have chosen A, B, and C, so now what kind of rotation should we do? So if you look at A, B, and C, A to B slant to the left, and then B to C also slant to the left. So a single rotation should do, because it's slant the same way, right? So what we should do is we should really do the middle node over here and promote that to the root. So it's like a right rotation on B, all right? So it's going to be a right rotation. On B, all right? Let me just highlight the part of the subtree that we should really pay attention to. This one here, B here, and C here. Okay, let me just try to show to you how you're supposed to do it, maybe in the test, right? Just in case you got this one here. So you can maybe sketch a little bit alongside. What you have is, let's say if you got, let me see if I got any space. Okay, how about here? If you got A here, you got B here, and also you got C here, right? That's exactly the A, B, and C situation we have. Each one of them has certain subtree, T1, T2, T3, and T4 in general, right? If you do it in order traversal, the order is going to be T1C, T2B, T3A, and T4. After the rotation, the in-order traversal sequence should remain the same. Otherwise, you're breaking the binary search property, right? Like a search property. Okay? So if you do like a right rotation, on B, so that means B is going to be now the new root. And then B here, and then because C comes before B, A goes after B, C and A, right? And then underneath it, so which two should we put? Well, T1 and T2, right? Which one should we put underneath A? So think about in order traversal. If I put T1 and T2, right? So up to this point, T1C, T2, T1C, T2, and then we go to B, and then we go to B. So far, the in order traversal is the same. So now what will be the remaining one? It's going to be T3, and then A, and then T4. So we got to make sure we got T3, and then A, and then T4, right? Got to make sure it's the same order. Okay. So we got T3, A, and then T4. Okay, so that's roughly what you have to watch out for. All right, and we did something very similar in the lecture. So now I just want to show to you very quickly. Can we identify T1, T2, T3, and T4 here? Yes, we can. Okay, so think about this is C, right? This part over here is T1. This part over here is T2. B is 60. So this one here is T3. And A is here. This one over here is T4. So luckily, they're all just external, right? Just luckily, right? Sometimes it may be some like a non-empty tree, subtree that you have to watch out for. All right. So let's do that. Okay. So I'll just redraw the tree. Otherwise, it's too messy to manipulate. Okay. Let me draw that quickly. So we still have our 50 here, 25, 10, 25, 1, and for 10, I got 15, here and here, and underneath 25, I got 30, I got 27, 27, I got this, okay? And let's now look at this part over here. So this is going to be the rotated version for this part here. Question, did I do something wrong?
You added 25 twice, it's supposed to be 25.
It's good that you stopped me right away. 25 here? Oh, I think okay, sorry. I saw 2 here, so I thought it's 25. Yeah, it should be 5. Thank you. Yeah, appreciate that. Exactly. Good. All right. That also tells you, right, if you do put something here in the test, don't just be careful, double check, right? Because that's really the color, there's the height, not really part of the number, okay? All right, let's now put it. So we pretty much know what to do. So we're going to put B here as the new root. So B here is 60, right? And then we're going to get the left of B should be C, which is 55. And then we're also going to get A. A here is 75. And in this case, we simply got external. All right, that's after a single rotation. But since the example said it's got to be multiple rotation, so that means after this single rotation here, the tree may not be balanced just yet. So we may have to do one more. In the actual test or exam, I may or may not tell you how many rotations might be needed. In general, you may have to go all the way up to the root, maybe, okay, in general, after deletion. For insertion, only one should be enough. Let's now double check. 0, 0, 1, 0, 1, 2, 0, 0, 1, 2, 1, 3, 0, 0, 1, 0, 1, 2, 3, 4, right? So far so good. You know, that part shouldn't change, right? So let's now take a look at here. 0, 0, 1, 0, 0, 1, 1, 1, 2. Did you spot something already? All right? 4, 2, 5. We do have unbalanced tree. Where? What is the lowest note that's unbalanced? Give me the number. 50? Yeah. Because if you look at that, under this 50 here, the two child notes here, 4 and 2, the difference is more than 1. Right? Okay, good. So now, what we should do is, let's identify that. This guy here should now be A. How do we choose B? The taller child. How do we choose C? You look at the heights. If they're different, choose the taller child. All right? Again, we got A, B, and C. It's got to be the similar rotation. Similar. All right? So, the last step. What kind of rotation should we do on which note? That's the answer I need from you. The last step. You want to try?
Right rotation on B.
Right rotation on B? Yeah, exactly, because they're kind of slant to the left, right? So you definitely want to promote 25 up as the new root. That's exactly what we did in the previous rotation. So this example, in some way, is kind of straightforward, right? Of course, it depends on the actual rotation. Sometimes the single rotation might be a left-right or right-left. So you may want to review that part as well, since we also did, that kind of a rotation, okay? Okay, so I agree with you. So let me just put as a notes here, but you can definitely complete it, okay? It's going to be, again, a right rotation on B. And of course, the B here is 25. In the previous case, the B is 60. Okay, put a note here. Yeah. Yeah, so try to just get kind of used to about, for insertion, basically what should you review about a self-balancing tree lecture? Why don't we take a look at the slides, right? Let me give you some guidance, like how I would study it, when I study. Of course, you got to study a little bit more detail if possible, okay? We still have time, don't worry. Okay, so for this particular lecture here, let's just go over very quickly, just fast forward to see what you should really review. This is kind of the lecture before the graph, right? So you definitely have to, of course, about the BST node, right? We kind of talk about how you can initialize some tree. I think at your tutorial, number 4 actually has some exercise on this, like in order traversal and also rotation. So take a look at the solution, it might help. Right, about searching, right? So the binary search we're considering always return a BST node, right? If the BST node happens to be internal, that means the key we're searching for exists. If the BST node happens to be external, that means the key doesn't exist, right? For good reason. Because when you try to insert something into the tree, and then if the node already exists, it's going to return back to the external node, that way you're supposed to insert, right? That's also something we go over. All right, so we talk about search, very straightforward. That's really 2101 stuff. And also searching, right? So some code example. So please take a look as well. That's also relevant, okay? And then we talk about, okay, in general, when you're trying to search through some BST, So the running time for searching, if you have no guarantee if the tree is balanced or not. So the best you can say would be it's going to be big O of h, which is the height of the tree. And we know that if there's no guarantee about a high balance property, h can be as bad as n, like a very slanted tree, or it can be as good as big O of log n, right? So there's a range. So that's why we really want to do rotation to maintain a balance, to make it to be big O of log n. Okay, searching, and then you can take a look at the slides, especially here, right? Just about some comparison here. You can take a look. Okay, insertion. So insertion, also look at the example we did. Actually, we did lots of examples for insertion and deletion. I think insertion is pretty straightforward. It's either the node returned by the search is either external or internal, right? That's something we talk about. Okay, insertion is pretty straightforward, but you want to pay more attention to deletion, especially about the different cases over here. I think for case number 1, 2, and 3, they're rather straightforward. Okay, just to see after the deletion how you're supposed to handle about the orphan trees, right? Well, whatever, there used to be left and right tree for the node that's being deleted. And case number 4 is where you have to exploit the search property, right, for the BST. Okay. So case number 4, that's something you definitely want to review. And then we talk about deletion, the various example, and then okay, balanced binary search tree. Okay, and we start with the high balance property, right? So that's the formal definition, and then we actually try to annotate, the nodes, right? 0, 0, the maximum of the high plus 1, right? That's what we did, diagram. High balance property. And then we talk about rotation, right? So the rotation, well, you can take a look at this one here. Is exactly what we drew, right? On the example. So this one is one example there, doing a right rotation. And then we also have the other cases. So this is really the steps, or you think about algorithm. We didn't really put it in the assignment to let you implement like how to do rotation. It's going to be a little bit more complicated than you might think. So we just didn't do it this term. So, but I think it might be more worthwhile your time to do some graph. But if you're interested beyond this course, you can definitely try. The steps are all there. You just got to handle some implementation detail. All right. So we got also single left. A single rotation that's left. Okay, also different example we did. And right rotation. Okay, the double rotation, right? So you can also go back to the notes. Let's say here. Let's say we have here, we got A slant to the right to B, and B slant to the right to C. So we basically got different slanted direction. In that way, we're going to need a so-called double rotation, but it's a single step we're going to complete. So you can think about eventually, we want to put the lowest node C and promote it 2 levels up. Okay, so after the whole rotation, C is now going to become the root right here. And then what goes underneath it on the left, underneath on the right is going to follow the in-order traversal order. Okay, so that's something I also explained during the lecture. You can also double check. All right. I think that's about basically what you got to pay attention to, right? Just the various details. And also the ones about how to do rotation after deletion, right? That's something you want to go over too. Okay, let me see. And that's it. Yeah, I think also pay attention to this slide here, 37. It's also about the running time, about asymptotic upper bound on the rotation for insertion and deletion. All right. Guys, any question? Any other question? I think we have 3 minutes if you want to ask me more. Otherwise, I don't mind letting you go early today. All good? All right. So the plan will be tomorrow, before tonight, 11:59 p.m., make sure you submit your best attempt for the assignments. Make sure you do that. And then I'm going to release the solution tomorrow, and then take some time before 4 p.m. on Friday to take a look at the solution. I'll see you 1:06 to go over parts of the solution for assignments. All right. All right. Thank you so much. And then I'll see you on Friday.